So, the waves test tomorrow has 29 questions. They are all multiple choice. The questions will be posted through a PDF on Google Classroom, and then you'll fill in your answers on a Google form. Content-wise, our big takeaway from this unit is that waves are a form of transferring what? Energy. Waves transfer energy. And they can do that in two forms. They can do that through a transverse wave or through a longitudinal wave. There are 8 or so questions that go into the difference between transverse and longitudinal waves. Transverse waves are light, whoops, and everything on the electromagnetic spectrum. So that includes radio waves, microwaves, infrared, X-rays, etc., etc. Longitudinal waves include sound. Transverse waves, such as light and the electromagnetic spectrum, require no medium. That means there's not any stuff that you need. Longitudinal waves require a medium. So transverse waves could be okay in a vacuum or in space, and longitudinal waves could not. The reason for that is transverse waves are up and down ones, like that. Longitudinal waves are the ones that are compressing and expanding. So this one is compression and rarefaction. And if you don't have any stuff, there's nothing to compress or rarefy. You have to have stuff in order to compress and rarefy that material. Stuff being air or water or a solid, but something has to be there to be compressed and rarefied. So those are our big differences between transverse and longitudinal waves, between light and waves on the electromagnetic spectrum, and sound. Now, you might not necessarily see the compression and rarefaction shown this way. You could also see it like tight spirals and then loose spirals, and then tight spirals and then loose spirals. That would be kind of like what we saw in our slinky, or something to that effect. Another way of thinking about this is that the motion of this wave is perpendicular. That means at a 90-degree angle. The motion of this wave is parallel, meaning it's going up, the energy is going along with the direction of the wave. And the compression and rarefaction is in the same direction as the energy motion. For the perpendicular one, the energy is going this way, but the wave motion is going up and down. All right, let's do a little sample. Another big idea. Another big idea here is that wave speed is equal to wavelength times frequency. So, if we have a graph that looks kind of like this, and I say, let's see, boom, 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 let's make this 6, 4, 2. Make this 3 and negative 3. And we'll make these meters. And we'll say that this is a sound wave, which I recognize would not be shown with a transverse piece, but it means that it has a velocity of 340 meters per second. Go ahead and solve out what would be the frequency of this wave. What frequency would be shown for this wave? For this one, step number 1 would be we need to take a look and figure out the wavelength of this wave. We could say that the wavelength goes from crest to crest like that, or I could count the total number of waves. In this case, I'm doing one full up and down in 2 seconds. We're just going to power through this one. So one full up and down in 2 seconds means you have one wave, in 2 meters. 2 meters, not 2 seconds. Excuse me. One full up and down in 2 meters means I have a wavelength of 2 meters. You also could have said I have 1, 2, 3 full waves in 6 meters. If I have 3 waves in 6 meters, that's a 2 meter per wavelength. Either way, you find that your wavelength is 2 meters based on that graph. Then I can plug my values into V equals wavelength times frequency. My velocity was 340 meters per second is equal to my wavelength of 2 meters times my unknown frequency. When I solve for frequency by dividing both sides by 2, I'm left with a frequency of 170 1/seconds, or 170 waves per second, which we call 170 hertz. So step number 1 is reading the graph, figuring out the wavelength that's shown on the graph. Step number 2 is plugging in and using our V equals wavelength times frequency equation and solving from there. Let's try another one. Let's say, okay, this one's going to be a little bit trickier. Now, I'm going to show you, this is going to be in time. This is going to be 3 seconds. And I'm going to do 1, 2. So that's 3 seconds in time. And I know that this also has a wave speed of 1.4 kilometers per second. 1.4 kilometers per second. See if you can solve for the wavelength. All right, so coming back, the first thing to note on this one is we're looking at time here. Since it's time, I can count 1, 2, 3, 4, 5, 6 waves in 3 seconds. 6 waves per 3 seconds gives me a frequency of 2 hertz. My wave speed was given at 1.4 kilometers per second. The tricky thing on this one is I'm using kilometers, which is not my standard unit. So I need to convert that to meters per second. There are 1,000 meters in a kilometer, so I'm going to multiply by 1,000. That gives me 1,400 meters per second as my wave speed. Wave speed is equal to wavelength times frequency. 1,400 meters per second equals wavelength times 2 hertz. Divide both sides by 2, and I'm left with a wavelength of 700 meters. You could also have listed 0.7 kilometers as long as you kept your unit in kilometers. All right, as long as you're diligent with your units, but it would be helpful to note that 0.7 kilometers is 700 meters. All right, so this part, the solving for wavelength equals, wave speed equals wavelength times frequency, that's our level 3 work. So that's where we really are trying to focus in terms of reading the graph, solving for one of those variables. Other factors that we're going to take a look at. Speed of sound. So the speed of sound is based on the stiffness of the material that it's going through. So that means it will be fastest in rigid solids and slowest in gases. Because rigid solids, like a very stiff metal, like aluminum, would be able to send that wavelength, or send that wave with a lot of speed. It sends that jolt really fast. The gas has a lot of flexibility to it, and so a lot of that energy isn't going to be sent quite as cleanly or as smoothly, so it'll travel slower. So when we say the speed of sound is 340 meters per second, that's in air. That's just about as slow as it can go. Sound will go faster in just about every other material or every other medium. Next, a few pieces that are really important to remember. Kind of 4 big vocab terms. The first one is the Doppler effect. The Doppler effect is when sound or light, waves generally, get compressed as they're coming towards you and spread out as they're moving away from you, or as the object that's creating the sound is moving towards you. So this is like the race car noise, meow, or the fire truck coming towards you and then past you. Sounds higher pitched coming towards you and then lower pitched moving away because the sound waves are getting stacked up and then spread out. So this is wave frequency increases coming closer, decreases moving away. Another one to remember is refraction. Refraction is bending of waves. At media changes. So that would be like between light and water, or sorry, between air and water. The light comes in like this, and then it changes its direction right there. It changes its angle. as it slows down or speeds up, changing its media. That's called refraction. And then the other two to remember are interferences, constructive and destructive interference. Constructive interference, we add the waves. Destructive interference, we cancel the waves. So constructive interference is going to lead to bigger waves. Destructive interference is going to lead to no waves or a canceled flat line. That would be like this plus this equals bigger. And canceling would be this plus that equals flat. Starting by going up versus starting by going down leads to some cancellation. All right, so that's pretty much what you need to know about waves for our wave test. We've got the Doppler effect, a few questions on that, a little bit of refraction, a little bit of interference, and then our big one is understanding what the electromagnetic spectrum is and then how to use that wavelength, frequency, and wave speed to compare.